Okay, so okay, so hello and good evening. Welcome to the third week of the PMRF and NPTEL session on signals and systems. I'm Shouharda Ghosh, and this is your Monday session for the PMRF for the NPTEL course on signals and systems in the version. Wait, let me check if the recording is taking place. Yeah, so it's over here, and let me go full screen. Okay, okay, so full screen. Yeah, fine. So we are in week 3. So in the previous weeks we have covered the fundamental preliminaries of the mathematics required to deal with this course. In that was in week 1, and then in week 2 we have covered with some basic time domain operations on the time domain operations on signals such as shifting, scaling, moving around with them, and some basic signals like the Dirac delta function and the unit step function. So today's session is on a very important topic. I mean, a core one of the most core contents of the signals and systems, that is frequency domain representation. So the contents that were covered in the previous in this week's lectures were frequency domain representation, that is the Fourier transform, and the rest of the course will deal around it and its variants. Then we talk about the definition of Fourier transform, followed by the Dirichlet's conditions, and these conditions define whether the Fourier transform shall exist or not for a given set of conditions on a signal. Then we also saw inverse Fourier transform, and finally a brief look at the frequency time uncertainty relation. Okay, so let's do a brief revision of the topics. Okay, so what was the topic? What was the definition of the Fourier transform? So if we have a signal x of t, and then we denote its corresponding Fourier transform by x of I shall use this capital omega subscript, because the small, although we are using small omega subscript in the lectures, but I shall be using this capital omega because in the subsequent upcoming far lectures in the later weeks, we will see where the small omega is used, and in order to avoid that confusion, I'll use this capital omega only from beforehand. And they form a Fourier pair. This x of t, this is the time domain representation of the signal, and correspondingly have a frequency domain representation, that's the x of capital X of omega. Okay, so how are they related? So for we have something called the analysis equation, which says that given a signal, we are now analyzing or breaking in the signal and seeing the spectral components. By spectrum I mean in this Fourier transform. So how does it look like? X of omega is integral over the entire real number line, x of t e to the minus j omega t dt. And what does the synthesis equation suggest? Which is, given all the spectral components, now you are putting them up together and getting the signal back. So that's xt is 1 upon 2 pi integral over the entire frequency axis x of omega e to the power j omega t d omega. Okay, so what does it say? So basically it constructs signals using complex exponentials e to the power j omega t. Okay, so all possible frequency complex exponentials are taken and they are combined in a weighted manner. And what are the weights? The weights are the x of omega. Okay, they are complex weights in a complex in using the complex weights, they are all summed up to create the signal. Okay, that was the analysis and synthesis equation. Now this is called the Fourier transform and the inverse Fourier transform. Now in order for the signal to have a well-defined Fourier transform, we have the Dirichlet's conditions. And what are they? The first one, the signal must be integrable over entire real line. And what's important? Absolutely integrable. What does that mean mathematically? Means that if I take the magnitude of the signal x of t dt, this should never blow up to infinity. So what is an example of a signal that is not absolutely integrable? So for example, we have a signal like x of t equal to 1 upon t. This violates this condition. Okay, then what do we have? The signal must have finite number of maxima and minima over given interval. Okay, and what is one example that defies this? So one example would be cos of 1 upon t. And how does it behave like? Well, so far around when t is very high, the frequency is very low, so it oscillates slow, and now when it goes around 0, oscillates very fast. Okay, so as t comes closer and closer, 1 upon t becomes very high, and but cosine always remains between 0 and 1, so it keeps on oscillating faster as t moves towards 0. So this is an example of a signal that violates this condition, violates the second condition. And the third one, the signal must have finite number of discontinuities over a given interval. Okay, so what that means is you can't have any signal that has a continuously having discontinuities like this. Such a signal always keeps on having discontinuities. You can refer to the lecture to have a better look at the signals that were shown. You might be thinking that there are some signals like sinusoid, sine omega t, that violates the at least the first one. Okay, so what is the problem with sine omega t should not have any, or cos omega t should not have any Fourier transform. Even u of t seems to be apparently violating this. So actually, since these are a class of important functions, these are fundamental building blocks, we treat them separately and use something called the generalized Fourier transform, which actually gives a relaxation on the first condition. Like x of t equal to 1 upon t, we can't say that these are fundamental or very important signal that we will be encountering daily, or in a signal processing perspective. It is not not a common practice to deal with 1 upon t, such kind of signals. I mean, they don't even exist. But signals like sine omega t, cos omega t, unit step function, these are fundamental signals that has to exist. Okay, so we deal with them, and so we have to create a different kind of a treatment for them. Okay, now let's talk about some properties, some very basic properties. So the first property of the Fourier transform is the linearity. So it suggests that if we have a signal a x1 of t plus b x2 of t, well, let's say x1 of t is a Fourier transform of x1 of omega, x2 of t has a Fourier transform of x2 of omega, then the linear combination has a Fourier transform a x1 of omega plus b x2 of omega. So how do we prove that? So let's say y of omega is integral over minus infinity to infinity a x1 of t plus b x2 of t e to the power minus j omega t dt. We break the summation and take out the coefficients, and we get the first Fourier integral and the second Fourier integral, and voila, we reach our result. And this actually makes sense, and this is actually simple, intuitive, because the integral operation, the integral is itself a linear operation. Okay, integral operation supports homogeneity, that is superposition, as well as the super linearity, which is superposition and the homogeneity. So this is a direct consequence of that. Now let's look at another property, that is the time shifting property. So if our signal x of t is shifted by a delayed by t0, then we have its Fourier transform as e to the minus j omega t naught x of, oops, I have to remain consistent with my notations, x of omega. Now let's prove that. So let's take yt as x of t minus t naught, and we see y of omega minus infinity to infinity x of t minus t naught e to the power minus j omega t dt x of t minus t naught to minus j omega t minus t naught. So minus minus is plus, so you have actually added it capital T naught, so we need to cancel that and add a e to the power minus j omega t naught term separately in dt. Now the variable term over here is t, so we can take this exponential out and use this t naught d of t minus t naught. So is a subtracting t naught from the constant, so the differential dt remains the same. So if we substitute it to z, we directly get the structure of our Fourier transform. So what do we get? E to the power minus j omega t naught x of omega. So a shift in the time domain results in a multiplication by a is complex exponential, and this property, this is the time shifting property. So there is a equivalent phase shift in the frequency domain. Now we look at, and delay is a very intrinsic characteristic of every system. So every causal signal will have this phase shift term in its spectrum. Now let's look at something called the modulation property. So I'll not talk about the real modulation, I'll talk about the complex modulation now. What does that complex modulation mean? Let's suppose I multiply my signal with some constant frequencies, complex exponential. I repeat, I multiply my signal x of t with a complex exponential, that is e to the power j omega naught t, whose frequency is fixed to omega naught. Then what do we have? Our spectrum x of omega shifts to omega naught. How do we obtain that? Y of omega is integral minus infinity to infinity x of t e to the power j omega naught t e to the power minus j omega t dt. Going further down, x of t to the power minus j omega minus omega naught t dt. Using this as the variable of the argument, get x of omega minus omega naught. So what does this mean? It means that if you have a signal whose spectrum is something like this, in the time domain, if you multiply it by this complex exponential, now let me tell you, complex exponentials do not exist on their own, I will show, as you have seen earlier, complex exponentials actually originate or give rise to cosine or sine. So we are just dealing with a part of it. E to the power j omega naught t. If you multiply this signal with this complex exponential, what we get is a shift. We shift this spectrum to omega naught. Okay, it has moved to a different frequency, and this moving or shifting to a different frequency is called modulation. Okay, so I think we have covered most of the properties, and based on this you will be able to solve the problems. If not, if you are finding any difficulty in solving the problem, then you can derive the property on your own. Okay, so let's move down to some previous year's assignment questions. Okay, so the first question was, determine the magnitude of the signal f of t equal to e to the power minus j omega naught t at a frequency omega naught. So what are they saying? We have this complex exponential, so we have to find this magnitude. It's a very simple question. I will show two properties. Let's see, if I want to find the absolute value or the magnitude, in that case what we do is the modulus of this complex number, and we very well know that mod of any imaginary number e to the power j theta is always equal to 1. So what do we get? Its magnitude is 1. If you want to look at it another way, then let us write f of t using the Euler property as cosine omega naught t. Since there is a minus sign, we will have minus j sine omega naught t. This is the real part, this is the imaginary part. Now if you want to take the magnitude of this complex number, that is the real part squared plus imaginary part squared, that cos square omega naught t plus sine square omega naught t, and that is 1. Okay, so, and that is the magnitude of the signal has been asked at a frequency omega naught. Now let me show you in a different way. This is the signal magnitude has been asked at a frequency omega naught. Okay, so now let me answer this from a perspective of Fourier transform. So let's say you have the constant signal x of t equal to 1. Then how does it look? This is a DC signal, right, whose value is 1. Okay, now if you take its Fourier transform, okay, what will it be? Fourier transform tells you the spectral components of the signal. Now you understand that this is a DC signal, and what is the spectral component of a DC signal? It's 0. It's a zero frequency signal. So since it's a zero frequency signal, we will actually have a delta function. At 0 we have, if we are using first, in case we are using the omega naught or the radian per second notation, we will have 2 pi delta omega, or if we are using the hertz, so let me write the units down, this is radian per second, and this is hertz. Then this will be delta f. Okay, so an important property to note is that the Fourier transform of the constant 1 is 2 pi delta omega, or it is delta f. Okay, very important property. And now what we are doing? We are doing the modulation. Okay, e to the power minus j omega naught t times 1. So what will happen? This is the modulation property. E to the power j omega naught t shifts the spectrum of x of omega. So what will this be? 2 pi delta omega plus omega naught. Okay, or it will be delta f plus omega naught upon 2 pi. Okay, so what will it be? If I look at omega, then at minus omega naught we will have a 2 pi strength signal, and if I are looking at minus omega naught upon 2 pi, from the f we have a single signal with strength 1. Okay, so the correct answer based on the options that were given, the options were 1, b 2, c 1 upon omega naught, d omega naught. So the correct option is option A, that's 1. Okay, now let's move to the second question. Determine the frequency spectrum of sine omega naught t. Okay, so it is just an extension of what we have done just now. What do we do? Sine omega naught t, as we noted earlier, can be written as 1 upon 2j e to the power j omega naught t minus e to the power minus j omega naught t. Okay, now what was this Fourier transform, and what is this Fourier transform? Its Fourier transform, we will use the modulation property, and we will find that this one has a Fourier transform 2 pi delta omega minus omega naught minus 2 pi delta omega plus omega naught. Okay, we cancel the 2's, and this is our spectrum. Now note that you will see a lot of options, and the correct option in that case, people, which you will be drawing for your exam sake, is this pi upon j omega naught and minus pi upon j minus omega naught f of omega omega omega. But let me tell you, in reality this is not completely correct, or in fact it's a wrong way of representing the spectrum. Spectrum has two parts. It's a complex spectrum. Every spectrum has two portions to it: the magnitude spectrum, that is mod f of omega, and the phase spectrum, angle of f of omega. Now why I'm saying this? That's because phase spectrum is a complex number, and every complex number has two real parts, so you always require two quantities to be shown, just as a complex signal. Okay, a complex signal has a real part and imaginary part. There are two things to be shown. Similarly, the spectrum always has two informations to be shown. That is, in a more you could have done it a real part and imaginary part, but that does not make much of too much of a sense in the real life. What we actually care about is the magnitude and the phase, because that gives a better picture of the signal. So what will the magnitude be? The magnitude will be at omega naught we have pi, and for the phase you have 1 upon j, that's minus 90 degree for omega naught, and for minus omega naught this is plus 90 degree. Okay, so phase and magnitude, you always need two components to be shown in a frequency spectrum. Okay, now what about, now the same thing has been asked for cosine of omega naught t. We can again repeat this exercise, so it can be written as 1 upon 2 e to the power j omega naught t plus e to the power minus j omega naught t, and then we have 2 pi delta omega minus omega naught plus 2 pi delta omega plus omega naught. Okay, and when you further simplify it, we get pi delta omega minus omega naught plus delta omega plus omega naught. Okay, and in terms of magnitude it's still the same. At minus omega naught and at omega naught you have pi, and for the phase is all 0. Okay, the phase is all zeros, 0 degree. Clear? Now let's move to the fourth question. Now we will be dealing with the system. So what have we been asked to do? Find the transfer function for the circuit. Okay, the circuit has a capacitor C and a resistor R. The input applied is Vi and the output received is Vo. So what is the transfer function actually representing? It's the ratio of the output to the input at a given frequency. So we are checking the frequency response of the circuit, how well it behaves at every frequency. So yeah, so we note how do we solve this. So this is a simple resistive divider circuit where you have Z1 as one impedance and Z2 as the other impedance. You are taking the output over here, so we write the output over here as Z2, sorry, Z2 by Z2 plus I think there's a delay in my screen's movement, so I hope there's no problem with my speech as well as I hope that you are able to understand and see simultaneously. I hope there's not too much of a phase lag between the two. So what is Z2 over here? Z2 over here is the resistance R. Z1 is our impedance 1 upon j omega c. Okay, so when I say Z2, that's R by R plus 1 upon j omega c. Multiply numerator and denominator by j omega c, we get j omega rc plus by 1 plus j omega rc. So our answer stops over here, but I will not stop the discussion here. I'll move it further and explain you how it looks like. Okay, so as always, every complex number gives you two information, that's magnitude and the phase. So this transfer function is also a complex number. Now let's look at, okay, so h of j omega, that's j omega rc by 1 plus j omega rc. Let's take its magnitude. So if I take its magnitude, the magnitude of the numerator, what is that? Simply omega rc, because it's an imaginary number. And the denominator, that's 1 plus omega rc upon whole square. Okay, that's the magnitude. And what's the phase? Phase is, numerator has a phase of 90°, denominator gives a phase of minus tan inverse omega rc. So for your convenience, the number a plus j beta has a phase which is tan inverse of b upon a. Okay, this is for your reference. We have used this to obtain the phase. Now, how do I plot the magnitude spectrum, or how does it look like when omega is very close to 0? Mod of h is around 0 by square root of 1 plus 0 square, that's 0. That means very small frequencies are not being allowed by this system. Okay, it does not allow. And why is that so? If you look at this circuit over here, we have a capacitor. Now we know that a capacitor provides very high impedance to DC signal. Okay, does not allow the flow. If you give a DC signal, the capacitor will charge and it will not allow current to flow into it. We don't have any displacement current over here. Okay, now if we make omega tend or approach to infinity, what will h be? We will not substitute omega equal to infinity here. We will see that h, the numerator remains omega rc, which is a very high number, but if you look at the denominator, it's 1 plus omega rc whole square. Okay, and when omega goes to infinity, the 1 becomes negligible in front of it. So what do we do in engineering as a practice? In such cases, we remove the constant and keep the variable term. Okay, so as you can see, the numerator and denominator are both the same, so that's equal to 1. Okay, so you see, and that's actually the maximum value that h of omega, j of omega can take place. So you see, it's a filter. It's actually a filter that does not allow or resists the presence of low frequency signals, but allows high frequency signals to pass through it. Okay, and this is actually called a high pass filter, HPF, high pass filter. What we have done just now is to analyze a system. Okay, here this is not a signal, this is a system. Okay, and we see that if we substitute h of j omega as 1 upon rc, okay, 1 upon rc means that frequency is 1 upon 2 pi rc, we get a gain of 1 upon square root over 2, is 0.707. okay, this is actually called the cutoff frequency. Okay, so how does the magnitude response look like? So initially it's actually very small. Okay, so let me tell you, what I'm plotting is actually the magnitude response over here. It's in a logarithmic scale. So initially up to 1 upon 2 pi rc, So actually the behavior is something like this, where very high frequency components are allowed. And let's say, okay, let me remove the discussion from here because we have not studied this. That's 1 over here, and that's 1 upon RC, where you have 0.707 inch. Okay, so you see high frequency signals are allowed, but low frequency signals are not being allowed. Okay, and now let's look at the phase. So at omega close to 0, the angle of H is 90 degree minus tan inverse of 0. What's that? That's 90 degree. Omega, when it approaches infinity, the angle becomes 90 degree minus tan inverse of infinity. And what is tan inverse of infinity? 90 degree. That's 0 degree. So what does it suggest? What does this phase shift suggest? It suggests that and actually if you substitute omega as 1 upon RC, the phase turns out to be 45 degree. Okay, yeah. So that's the transfer function of the circuit, and a brief discussion on how the magnitude and phase looks like. And what does it actually suggest? So it suggests that if you have a signal A sine omega naught t and you pass it through this circuit C 1 upon this is R, then we get another sinusoid only with a new amplitude and a phase shift. Okay, where the new amplitude is the old amplitude times the h of j omega, that's omega naught RC by square root of 1 plus omega naught RC whole square, and phi hat, that's 90 degree minus tan inverse omega naught RC. Okay, and moreover this phase shift suggests that if that each of these frequencies will be shifted by different phases. Okay, I can talk about this, I can take this discussion to a great length, but I will stop over here because it will deviate too much from our present discussion on Fourier transform. Sorry. So the fifth question is the Fourier transform of e to the power minus 8t is not possible because, okay, so I shall not give you the options now because if you look at the options it's very clear, but then let me go step by step. Okay, so we look at, whenever we say that a Fourier transform is not possible, what do we check for? We check for the Dirichlet's conditions. The Dirichlet's conditions have been given over here. The signal must be absolutely integrable over the entire time interval. Signal must have finite number of maxima minima over a given interval. Signal must have finite number of discontinuities over given time interval. Okay, so what do we need to do? Our first job is to plot the signal. So let us assume that A is greater than 0. Then how does the signal look like? The signal looks like this. Okay, so you see 0.2 holds, okay, because there is no maxima or minima. Okay, these are all asymptotic values. Okay, there are no local maximas, no local minimas. 0.3 also holds because exponential does not have any discontinuity in it at all. Now we look at point 1. Point 1 says that integration over minus infinity to infinity modulus. Now see the modulus, this is always a positive number, so we do exponential is a positive number, so we don't need to take its modulus. Now I say t dt. What is this? This is the area under this curve, and this goes to infinity. Because the integral is infinite, it is not absolutely integrable, which violates our point 1, and that's why we do not have the Fourier transform of e to the power minus at. Okay. Okay, so now we try to find the so I guess we I mentioned also that for the signal 1 the Fourier transform is 2 pi delta omega. So for any magnitude a, the Fourier transform will be 2 pi a delta omega. Okay, just as a point of revision. Okay, now we look at Fourier transform of this signal, which starts from minus t by 2 and ends by t by 2, and there is an amplitude 1. Okay, this is called the rectangular signal, and is often denoted by in this way, or in some books you may see this kind of a representation, or some people, every people have their own way of representing this signal. So wherever you are solving problems or looking for papers, okay, you need to look at the definition that they have given accordingly. Fine. So now we are supposed to find the Fourier transform of this signal, and this is a very critical signal. Okay, it's a rectangular pulse. It is a simple signal, but this will give us very important highlights about spectrum analysis. So x of omega is the integral of the signal in times the exponential. Now where does our signal range from? Our signal ranges from minus t upon 2 pi to t upon 2 pi, and assumes a constant value, that's 1. We have our exponential here. Now we integrate this exponential with respect to t, so in the denominator we have minus j omega. Now the value ranges from minus t upon 2 to t upon 2. We substitute these values and we get e to the power j omega t by 2 minus e to the power minus j omega t by 2 divided by j omega. Okay, so now we have a popular form that is popping in front of us. We shall be using this. So as I had mentioned in your first class, that this is a very important property which will keep on coming up again and again in any signal processing course that you take. I mean signal processing courses that involve deterministic signals, or signals where you have such spectral analysis. Okay, so what do? We take out 2 and omega over here, exponential j omega t upon 2 minus exponential minus j omega t upon 2 by 2 upon j. Our theta is omega t upon 2 over here, and hence I can write it 2 omega sine omega t upon 2. Okay, now I can further write this as t 2 omega t sine omega t upon 2. Further simplifying this, t sine omega t by 2 omega t by 2. Okay, this expression sine x upon x, let me tell you, as I have as I had been a student myself and gone through various courses during my undergrad as well as in my recent encounterings as a TA in signals and systems courses, I have seen different books writing different expressions for the same formula. Okay, so for example, sine x upon x. Okay, in some places this has been written as the sampling function. Okay, so you write it as sampling of x. In some places you will find this written as the sinc function. Okay, some books, some standard books like BP Lathi's books write sinc x as sine of x upon x. Now the funniest part comes, in some books, I don't remember, I mean some other books like Papulis or some others like maybe even uh, Oppenheim, they write sin x as sine pi x upon pi x. Okay, so you see there are two definitions, I mean you see two contradictory things. So what should be, the form is the same, the shape of this is function, if that which I will be drawing very soon, is almost is the same, the structure, the shape is the same. Okay, I'm not saying the exact positions, but the shape is the same. But if you are dealing with evaluatory courses like your semester courses or this NPTEL courses for sake, okay, you should be careful about the notation which they are using in the course, and you should remain consistent with that. That's my advice. As a student, you should be careful, you should always know what your instructor or what the course material follows. Okay, so you cannot in this in such evaluatory scenarios you cannot follow your own mindset. Okay, so what I guess is followed in this course, just confirm from the video lectures, is that they follow this notation most likely. Just requesting you to please check it with the lectures. Most likely they follow this, and if I follow this, then I can write this t as sinc omega t upon 2 pi. Okay, so how does the sinc function look like? So let's see, let me do it for once and all. How does the sinc function look like? So if I do sine pi x upon pi x, at x equal to 0, it will be for assume a 0 upon 0 form, and then you apply the L'Hopital's rule, you have to achieve the value 1. It goes down, it has a 0 crossing, it goes up, 0 crossing, goes down, and it keeps on oscillating and dying. Similar thing happens over here, it keeps on oscillating and dies. Okay, what are the 0 crossings? The most important part of the 0 crossings. 0 crossings are sine n pi equal to 0, x equal to n, where n is integers like plus 1, plus minus 2, plus minus 3. This is 1, this is 2, this is 3, this is 4, and so on. This is minus 1, this is minus 2, this is minus 3, and so on. Okay, now if we so you see, if I draw sine x upon x, the shape, let me remind you, shape is a different, what I'm talking about is shape. The shape is still the same. The 0 crossings are at pi, 2 pi, 3 pi, so on. Integral multiples of pi are the 0 crossings of this sinc signal. Okay, so when I'm talking about t sinc of omega t upon tau, so your spectrum is looking like this. Okay, so what is happening over here? you have a signal which lies in a finite duration. Okay, you have a signal that you have constrained in time, but in frequency it spreads out. Okay, it has no limit, it has no bandwidth. Okay, it's an infinitely spread signal. Okay, so you see this is an uncertainty, right? So if I have a time domain signal that I push up like this, it has in frequency domain it spreads around. Now there is something called the duality principle, which suggests that if we have a signal xt with a spectrum x of omega, capital X of omega, now if I take capital X of t, that means I use this function in time domain, then it has a spectrum 2 pi x of it is this x. Okay, let me use different colors. X of t gives me x of omega okay. So what does that mean? If I have a signal which is unlimited in time, then it gets constrained in frequency. Okay, so it gets limit in frequency. This is actually what is called the time frequency uncertainty. Okay, you can never have a signal which is both limited in time as well as in frequency domain. Okay, so this is the direct signal and the corresponding looks like. Okay, so we have omega t upon tau, so we'll have crossing set 2 pi upon t, 4 pi upon t. Okay, minus 2 pi upon t, minus 4 pi upon t. This is an infinitely band limited not a band limited signal. Its spread goes on, but you can assume that most of the information is contained in this half. Okay, then this was the question number 6. Now let's look at question number 7. And what is that? We have a signal ft is e to the power minus at ut. A is greater than 0. How does it look like? First of all, we have to find this Fourier transform, but before that, let's plot the signal first. So initially it is 0, it suddenly jumps up to the value 1 and then it decays. In the same way, we have the decay for different values of a, they will decay differently. So you see here that this actually happens with increasing a. As your a goes up, your decay becomes faster. Fine. And where do you observe such signals? So for example, radioactive decay of nuclei, or let's say discharging of capacitors in DRAM cells. So what are although it's a electrical engineering signal processing course, but the extent of these waveforms are not just limited to the electrical engineering scenario only. It's wide, it's present all over. So damping due to fluid. Okay, discharging of capacitors in DRAM cell. What does it mean? Our computers have RAMs, right? So we have SRAM, DRAM in various positions of the memory hierarchy. So DRAM cells are actually consisting of a transistor and a capacitor. So when you discharge this capacitor, then they have when you are erasing data or writing data into it, so there may be a writing or reading of zeros and ones in writing of zeros and ones into the cells which store your information in bits, zeros and ones. So if you are writing 0 to 1 of the dynamic DRAM cells, then this is the waveform of the voltage that takes place in the DRAM cell, DRAM cells capacitor. Okay, so now how does its waveform look like? Sorry, how does its frequency transform look like? So we directly evaluate it. Since it starts from 0, we start the integral from 0 and remove the ut sign. T dt j omega t j omega 0 to infinity. Once we put in the limits, we get 1 upon a plus j omega. Okay, now again we need to look at magnitude. The magnitude is 1 upon a square upon omega square, magnitude of this simply. And the phase is 0 in the numerator. We subtract the denominator phase. What is the phase of the denominator? Minus tan inverse omega upon a. And how do they look like? Okay, so you see that this signal also has low frequency contents, and high frequency contents are becoming lesser and lesser in this. So you see these are the low frequency components present which have a higher presence. And these are the high frequency components which have present in lesser quantity. Okay, so this is actually the spectral analysis of an signal. Now let's look at another signal. F of t is e to the power at u of minus t. Okay, now how will it look like? First let us draw e to the power minus e to the power at. E to the power at will look like this. U of minus t is 1 when t is less than 0 and 0 otherwise. You multiply the two and you get this. This is simply the mirror image of the original the signal over here that you are seeing over here. Okay, so this does not occur in real life, but we are doing this for some mathematical purpose, which I will show you soon, and also for your practice. So what is its spectrum? F of omega is integral over minus infinity to 0 e to the power at e to the power minus j omega t dt. 0 to a minus j omega t dt a minus j omega 2 minus infinity. What does it turn out to be? A minus j omega. I won't discuss its phase any further. See, oh yeah, I will discuss about this phase spectrum. You look at this signal exists for t less than 0. That's an anti-causal signal and which does not exist in real life. You look at its phase f of omega. What's it? Minus of tan inverse of minus omega upon a. Tan inverse of omega upon a. When you plot it, what will it look like? It will look like this. It has a positive phase. Now if we look at this signal, this is a signal that exists less than t and greater than t also. Okay, now we observe that its phase is 0. Okay, 0, or it will be when you will have phase reversal, then it will be 180 degree, but actually you see it's nothing beyond that. Okay, so it's a non-causal signal. So non-causal signal has almost a 0 phase or a 180 degree phase. The anti-causal signal has a positive phase, and real life signal, like be it over here, it has a negative phase for omega greater than 0. Even this x of t minus tau, okay, e to the power minus j omega naught t, this also has a negative phase. So real life seed stems have delay, and that delay corresponds to a negative phase in the phase spectrum. So this is a very important thing to mind, that real life signals are actually causal signals, which means that x of t is 0 for all t less than 0. Okay, and what do they imply? It means that their phase is positive for omega less than 0 and phase is negative for omega greater than 0. Such signals are realizable, and it's a very important property to keep in mind. Okay, so we noted this down. Okay, so let me revise the signals that we had taken. We had taken this signal, this e to the power minus at ut, which had as transform 1 upon a plus j omega. Then we took the signal e to the power at u minus t, that had this a minus j omega spectrum. Okay, now I will form two signals from this. Okay, the first one is directly the addition of the two. Okay, and what we how can we write it? We actually write it as e to the power minus a modulus of t. Fine. And so what will be its spectrum? 1 upon a j omega plus 1 upon a minus j omega. If you simplify them, you will get 2a by a square plus omega square. Again, you see, this is a non-causal signal over here. It exists before 0 and after 0 also. So you see its phase is also 0 degree. So a clear understanding, it's not a real life signal, it's not a causal signal, hence its phase is 0. This is an important signal to keep in mind. E to the power a minus a mod t, that has the spectrum 2a square plus omega square, which was obtained by sum of f1 and f2. Fine. This is actually very important. This e to the power minus a mod t and all these are very important from an exam perspective. Now let's talk about another signal, which is f1 minus f2. So how will it look like? It's a kind of an anti-symmetric signal. It's an odd signal. Fine. So it's okay. So what will its transform be? 1 upon a plus j omega minus 1 upon a minus j omega, a minus j omega minus a plus j omega, a square minus j omega whole square, that's minus 2 j omega a square. So this is e to the power minus 80 minus e to the power 80. Okay, square plus omega square, 2 omega by j e square plus omega square. Okay, this is also an important property to keep in mind. Now I will show you something interesting. Okay, we told you that as a becomes higher and higher, okay, as a becomes higher and higher, it becomes sharper. But if I move a to 0, what will happen? E to the power minus 80 will become 1. E to the power minus 80 will become minus 1. Okay, so what is this signal? This signal is actually called the sine function or the signum function, which is 1 for t greater than 0 and minus 1 for t less than 0. Okay, so this one, if we let a tend to 0, what are you getting? We get y of omega as 2 j omega, 2 omega by j omega square, and that's 2 upon j omega. Okay, so signum function has a frequency response 2 up by j upon omega, 2 by j omega. So this is also a very important signal which you will be encountering in your practice questions as well as in exams. And in fact, if you have to find the Fourier transform of unit step signal u of t, it's not easy to find. What we actually do is this unit step signal, you remember that we had broken it into that in our previous classes we had learned how to break down a signal into its even part and its odd part. Okay, so the even part of ue of t will be half of ut and half of u minus t. Okay, u odd part of t will be half of ut and half of minus ut. So uet is a DC signal half, u odd of t is half the signum function, half the signum function. All right, now we have found their corresponding, we know the delta, we know the Fourier transform of this is a DC function, so it's a delta. Similarly, we knew its Fourier transform, the signum function, that's 2 upon j omega. Now we can evaluate this and find the Fourier transform of u of t. Okay, this is actually a part of your assignment, so I'm not stating the answer directly as per the rules amended by the NPTEL system. Okay, so I hope we have covered enough for today's session. Let's revise whatever has been done till now. Okay, so we looked at so this week's contents covered frequency domain representation, that is the Fourier transform. There was a definition of the Fourier transform, followed by the conditions for that define whether the Fourier transform shall exist or not. Then there are some exceptions to that conditions. Then we had talked about the inverse Fourier transform, followed by frequency time uncertainty relationship. Okay, so this note shall be shared after the I close this. So thank you everyone who have stayed in the meeting for the entire session. Thank you for your patience, and thank you for everyone who is watching this video online. Thank you. Have a nice day.